All right. Yeah. Thank you very much. Yeah. Thank you very much, Eleni, for the nice introduction and for the invitation to the seminar. So to give just a bit of short context, I've done my PhD in 2011 in applied mathematics already at INRIA in Rennes. So the INRIA Institute is now called the French National Institute for Research in Digital Science and Technology. So we are a public research institute in France, with several branches. After that, I've done 2 postdocs, and since end of 2013, then I'm a permanent researcher at the institute. I'm working in the IFRS research team, which basically means inference for structures, statistical inference for structures. It has a longer abbreviation in French. For structural monitoring, and we are a joint research team between INRIA and the Université QCFFL, which was formerly IFSTA, and we are located between Rennes and Nantes and have about 10 permanent researchers in the team. So our main focus is data-driven methods, statistical methods for data-driven, and a bit of model-based damage diagnosis, model analysis, damage diagnosis for structural health monitoring. So for the general context again, so we suppose that we have a structure that has some physical parameterization theta. We collect vibration measurements of the structure, and our 2 main axes of research are one, the system identification, so to obtain estimates of the parameters with its statistical distribution properties, and the other research axis is then to detect changes based on our vibration data in the properties of the structure by doing statistical tests. So, but without identifying the parameters. Then. So I will talk a bit about both today. So for the basic assumptions, so we suppose we have sensor data under unknown excitation in general. Our models are linear, our structure models are linear, and we usually work with the state space models. Because they are very nice methods to analyze them and to obtain the structural properties based on them. So one problem is then the identification of our vibration characteristics, including the statistical analysis of the estimates, and the other one is the damage diagnosis. And for the damage diagnosis, then we also try to make a link between the data and some model parameters, but the focus is still on the data-driven analysis. So in the first part of this talk, I will consider the uncertainty quantification for modal analysis with subspace methods. So we use, we very much like to use the subspace methods for our identification problems because they are they're parametric, they are direct computation, they are very efficient. So we don't need optimization problems to solve for that. So they are fast. And they also have very nice statistical properties, being consistent even under non-stationary excitation, which we always have in practice. And we know the statistical characterization of the estimates. They are asymptotically Gaussian, so we can derive also the uncertainty quantification schemes for their estimates. And moreover, we can also use them in the context of detection, because with the subspace properties, we can have a common framework for the identification and the detection. Yeah, so they are very suitable for vibration analysis. Then just to give a quick outline of the subspace methods in general. So if we have our data, our output data yk, we want to obtain the system matrices A and C of the state space model because they contain the dynamic properties of the system. And to do that, our initial step is to compute the output covariances of the data. So there are tons of subspace methods in the literature. Here I just focus on this covariance-driven one. So first step is to obtain the output covariances of our data, put them into a Hanker matrix, and then we have quite direct operations to obtain then matrices A and C. So we start with the SVD of the Hanker matrix to obtain observability matrix of the system, and from there we can obtain matrices A and C then from the least square, and go to the eigenvalues and eigenvectors of the system from there where we find our modal parameters. So then, we have with the subspace methods, we obtain point estimates of our modal parameters. But what we are interested in addition is also to get their statistical properties, because when we have estimates, they change with every data sets. We have noise. So one important problem is to obtain confidence bounds of those model parameters, and for that we've worked quite a lot in the last couple of years to obtain methods for the uncertainty quantification of those estimates. So here we are also talking about data-driven uncertainty quantification. So, and why is that important? Yeah, because that helps us to assess the quality of estimates with the proper confidence bounds. If we want to compare modal parameters between different data sets, well, that would be meaningless without having uncertainty bounds, because you wouldn't know if it's just a natural fluctuation due to the intrinsic uncertainties, or if it's a significant change due to some change in the system. And then our modal parameters are inputs for diverse applications, for tracking, for FE model updating, for damage diagnosis, etc. So our uncertainties with which we estimate our initial modal parameters also play a role then in those applications, because they will make our results somehow uncertain. So it's important to assess them right from the start. And the uncertainties that we are talking about here are due to the identification problem itself. Because first of all, our system inputs are usually unknown. We assume that there are some noise, some white noise, colored noise coming from the ambient excitation. We have measurement noise, and our data is of finite length. Yeah, and this all makes that our estimates have some statistical distribution that we would like to analyze. And for that, our goal is to have the estimation of our modal parameters and their variance from the same data set. So we don't do sample statistics for getting uncertainties of a frequency that we could get from 100 data sets, let's say, getting 100 frequency and doing sample statistics. But that's just not possible in practice, or that's not the goal in practice, because sometimes we just have one data set and we want to get the frequency and its uncertainties from our data set. And even if you had several data sets, doing all the tracking of the same modal parameters throughout all the data sets, it's just not practical for the applications. So the strategy for doing our variance estimation is a mixed empirical analytical approach, because we have to start somewhere with a sample covariance. And for that, we go back to the start of the subspace methods, where we calculate our output covariances. Because we can very easily get a sample covariance of our output covariance of the data. We can take our data set, cut it into pieces, evaluate auto covariances on each piece, and get a sample statistics of the auto covariance like that. And that's easy to do. And then our modal parameters, or whatever we compute from there, they are a function of our auto covariances that we have at the beginning. So we can analytically determine the sensitivity of our parameters with respect to our auto covariances. And that's not so easy sometimes, but it's still very feasible to do, because we know all the steps of the algorithm, so we can go through the analytical sensitivities and compute them then on the data. And like that, we can propagate our covariance from our initial output covariance down to all the steps in the algorithm to the modal parameters. And if we have our sample covariance of the output covariances and our sensitivities, then we can obtain the covariance of our target parameters that we compute from the beginning. And that this works is, and the theoretical justification of this approach is the delta method in statistics, and the fact that nearly everything that we estimate from our data is actually asymptotically Gaussian. And that's like the fundamental premise that we have, that our initial estimate that we get, for which we compute the variance of, that this is a Gaussian variable asymptotically. So let's say that the x hat up there is our covariance estimate of the data, or auto covariance from the data that we compute. So if this is a Gaussian variable asymptotically, well, that's our starting premise, so that the error between the estimate and the true value is getting asymptotically Gaussian when we increase the number of data points. then we calculate a function of our initial variable, of our initial asymptotically Gaussian variable. We can do a Taylor expansion of that function in our theoretical true value. So that's just the first order Taylor development. And then if the first derivative here is non-zero, well, then also the function of our random variable is also asymptotically Gaussian. That's the first fact. And the second one is that the covariance of the function is exactly our derivative of the function times the covariance of the initial variable times the derivative transpose. Yeah, and that is due to the fact then that if we have always a factor of square root of n around here, which is the data length that we use, so our data length goes to infinity, then all those asymptotics hold. And with its square root of n, our arrow and Taylor expansion will get smaller and smaller and disappears. So everything is still Gaussian then. And actually, our auto covariance, our output covariances that we compute at the beginning of the subspace algorithm, they do satisfy our central limit theorem up there, because they are a kind of mean over the data points, and under standard conditions, under certain conditions, those means are asymptotically Gaussian. And here it's the case because we have a mixing process, our system is stable, so this makes that those covariances are Gaussian. So we can start with their sample covariance computation and then just propagate everything through the algorithms, and everything else is Gaussian as long as our derivative is non-zero. So that's for the theory. In practice, we have to pay attention a bit also to the implementation, because then those covariance matrices can get huge. So we've paid some attention to fast and memory efficient implementations, exploiting then the structure of our initial sample covariance estimate, then exploiting the symmetries that we have here. And also for modal parameter estimation, when we compute stabilization diagrams, because we have when we estimate modal parameters from data, we never know the true model order, so we just try out several ones. And that also has a certain structure to it in the computation, so we can end up with some quite efficient tool for the computation then of the uncertainties of the real variances, and have computation times then of a few seconds to a few minutes for the variances and for realistic problem sizes. So here just a few examples. The well-known Z24 bridge. So when we get the uncertainties in the modal identification is on one data set, we see them as horizontal bars then here. And so we have the plot of the natural frequencies versus the assumed model order. And the modes or the frequencies that are structural frequencies, they are assumed to be stable over different model orders, so we can select them from them. And so there are the physical modes. There are also spurious modes from the noise. And usually those spurious modes tend to have a high uncertainty, so we can simply also put a threshold on the uncertainties and getting some nice diagrams to analyze. Yeah, we can do that for the frequencies, for the damping ratios, for the different model orders. Use that then as tools for getting global estimates, then like a weighted mean with the uncertainties over all the different model orders to get some meaningful final result. And use that as a tool then for diverse applications. So in the last couple of years, we worked on methods then for providing the uncertainty bounds then for diverse subspace methods. I mean, there are input-output subspace methods, output-only subspace methods, data-driven ones, covariance-driven ones, and we came up with the framework then to being able to compute the appropriate sensitivities then for the uncertainty quantification. More recently, with Simon, we've worked on the uncertainty quantification also of the input matrices then that are useful for transfer matrix estimates and their uncertainties. So here, for example, we see the uncertainties of the magnitude of the transfer function then computed with those techniques. Simon was also working with us on the uncertainty of modal indicators. which is then technically a bit a departure from the first order framework, because those modal indicators are bounded. And the first derivative actually becomes 0 then in the Taylor approximation. So, but the second order framework then works very nicely with that, and is useful then also for monitoring and other applications. So these are the basic tools, and also Simon made some nice validation to see that okay, it's not only the theory that works fine in the simulations, but also the application then on data from the lab. At least have a validation then on the accuracy of the methods for real data. Yeah, then the uncertainties that can be useful for diverse applications where we compute stuff on our model parameters, like for example for damage localization method, the DLV damage locating vector method that Dennis Brunel was proposing in the past. So an input to those methods are the model parameters. Since they have some uncertainty, we can propagate the uncertainty also through the methods, and actually can show that with a proper weighting by the uncertainties themselves, we end up with more accurate results than regarding damage localization, for example. Also for some applications for FE updating, since when we want to update parameters based on the modal parameters, and our modal parameters are uncertain, the results also have, we can propagate it through to the uncertainty of the parameters to analyze the contribution of our modal parameter uncertainties then on the updated parameters. And we also can, in the last contribution here, actually use the modal parameter uncertainty directly within the updating process. Because we know that we cannot be better with our estimate than the whole uncertainty bound that we have, because we have our probability of 95% that we are around some confidence interval. So we can use that information also in the objective function in the updating process and as a stopping criterion, or also with then defining a stopping criterion at the end. And here, for example, we have a figure of an objective function for the updating, and everything that is in the valley then is, like, from a statistical viewpoint, equally acceptable. So once we end up there, we can stop the algorithm and are much faster than really going to the minimum that is not really meaningful, because well, you're uncertain anyways. Okay, and the methods are also, or some of the methods are also part of the Artemis toolbox. Okay, so that was the first part on the quantification of the uncertainties in the estimation. And the second part of my talk is then concerned with statistical damage diagnosis, well, where we also consider the uncertainties related to the data then in the diagnosis approaches. So for the general context here, I will present some results on damage detection and localization, data-driven, basically, with some extra model information. But the overall premise is to be data-driven. So for detection, to answer the question, is there a change in the structure? Is the structure damaged? For localization, then where is actually the damage? And the overall premise is to compare vibration data from a reference condition to current data that we collect. So for that, we assume that we have some parameterization of our structure available that is related to some local damage parameters. So usually these are model-based parameters. For example, well, and that really depends on our actual problem for damage diagnosis that we want to perform. So if you talk, for example, about finding marine growth on an offshore structure, then that's about added mass on the structure. So then we would choose some mass parameters, for example. Or if you talk about cracks, then that's related to some stiffness parameters. So our parameterization of the structure contains those local parameters then for elements or for groups of elements of our model. And the goal is then to determine small changes from our reference parameter theta 0. So theta 0 is a parameter in the reference state. And so in the reference state, we assume that we have our parameter theta 0 known, and we have data available from the reference state. And our parameter in the current state, for which we want to analyze the system, is unknown, and we have data available also in that state. Yeah, and for the damage characterization, we do not want to estimate the new parameter in the new state, but we rather want to ask or answer the more simpler questions than, has our parameter changed or not for the detection, and which components of the parameter are changed without knowing the parameter then for the localization. So for that, we have we have two statistical frameworks that I want to present. The first one is quite an old framework that we have in the team for many years now, which is called the asymptotic local approach. So for that damage diagnosis framework, we start with a Gaussian residual vector that is computed on the data, and that is parameterized with our system parameter. Then to analyze or to decide about the current state, we assume closed hypothesis and make a generalized likelihood ratio test then for test statistics then to determine the change in the system. So starting with residual vector. So for that we have a damage sensitive feature vector zeta that is computed from the data, and that is quite general also. And it just needs to have a zero mean in the reference state and a deviation from a zero mean when damage appears, when there is a change in the system. And for that, there are tons of features also available in the literature. And another condition is that it needs to be asymptotically Gaussian for the statistical analysis. But as we've seen before, when we compute those indicators from data, in many cases, they are actually Gaussian, asymptotically Gaussian. Examples are, for example, we can take a modal parameter difference between the current state and the reference state. We've seen that they are Gaussian, so that can work as a residual. And when we talk about the subspace identification, we can actually go a step back and define a residual directly on the subspace properties of our anchored matrix H that we've seen at the beginning, that is filled with the output covariances of the data, because this matrix contains the dynamic properties condensed of the system. So we can compute our anchored matrix H in the current state of the system, re-multiply it with its left null space that has been computed in the reference condition of the system. So if our system is in reference state, this product is zero. And when the dynamics have changed of the system, then the product becomes non-zero. And this has also the advantage that we don't need to do modal analysis in the current states, because we just can compute this product and have a comparison of the system dynamics. So these are examples of such a residual vector. And then to analyze it and for changes, we have the definition of such closed hypothesis, where our null hypothesis is that the current system parameter equals our reference parameter when we are in the reference system. And if we have a change, if we have a fault in the system, then that's different from zero, where the difference term delta over square root of n is quite particular in that setting. But the purpose of such a definition is actually it's a mathematical purpose at the end, in order to be able to describe mathematically correctly the asymptotic properties of the residual in both the reference states and in damage states. So it can be shown mathematically that if we have something like that under quite standard conditions, that's me? Ah, okay. That under quite standard conditions, if we do something like that, that our distribution of the residual under the alternative hypothesis actually has a mean that is related to J, which is the derivative of the residual with respect to parameters, times this vector delta that is up there. So that gives us a proper characterization of the statistics of our residual in both states, where we have a change in the mean between reference and damage states, and then easily derive the tests in such a Gaussian framework afterwards. And another nice feature of this framework also is that, that since this depends on the data length n that we use, if we have lots of data available, that also means that the change in the parameter between the current state and the reference state gets smaller and smaller. That is detectable at the end. Yeah? So if n grows, data minus data 0 can become quite small. And we still have the same delta here for the mean of the residual, which also makes sense statistically, because if we have lots of data, while we have lots of confidence in our data or in the stuff that we compute from the data, so we can also detect smaller changes because we have more confidence, we have less variance. So that's that's a nice feature of the framework. And since our distributions are Gaussian in the reference and damage states asymptotically, to decide now if our residual that we compute on new data, if it's more likely that it belongs to the reference distribution or to the damage distribution, a standard tool for that is the generalized likelihood ratio test. That tests delta equals 0, so change is 0 against the change is non-zero. And we end up in such a test statistics involving then the residual zeta, its covariance sigma, and the sensitivity towards the damage parameters j. And so it's a weighted sum, it's a weighted product, a weighted square basically of our residual. So since it's a square of a Gaussian, it's somehow k-square distributed. So we know its distribution properties, we know its degrees of freedoms, and one can easily show then also that so if we have no damage, then we have a central k-square distribution. If we have a change in the system, if we have damage, we get a non-centrality parameter that is then linked to the change vector delta. Yeah, so we have a distribution in the reference state that looks like that. And if damage grows, well, then the non-centrality parameter gets bigger. So the distributions are separated. So we can set up a threshold on the reference state to decide then, okay, are we are in the reference or not? And so we can, based on the allowable probability of false alarms, we can set up a threshold in the reference state. And then when new data comes in, we compute the test, compare it to the threshold, and if we are over it, then we are damaged. Or we decide that we are damaged. So to show a few examples, here we have a bridge, the S101 bridge, which was a benchmark of a European project that got damaged during 4 days. So we have lots of data available during all the damage tests from the 4 days. And in particular, one of the columns was cut through, lowered in 3 small steps. Then it was uplifted again, and then cables were cut through. So we used some data before the cutting started as a reference data, and then just computed directly on the data sets. So we had like 700 data sets during those 4 days of testing. And for each of the data sets, you see in the timeline on the horizontal axis, we computed for each of the data sets then the test statistic for the damage test. And you can see quite clearly here then the 3 steps of the lowering of the column, the damage got bigger. And when the column was uplifted again, well, then the test value goes back, but it doesn't go back to the original value, because in the meantime some cracking appeared in the structure and so on. So so we can see that the test reacts with the damage. That's also part of the Artemis toolbox. And something that I haven't mentioned so far is that, I mean, those tests, they are aimed at detection, but we can actually also make some focus tests on each of the different parameters that we have in our parameterization, and then decide for the different parameters, or for each of the parameters in our parameterization, if they have changed or not, then with the purpose of damage localization. And here we have an example for the localization then, actually the yellow frame, which was also a benchmark in the US, that has 32 braces, so those braces here, of which some were removed then for a damage test. So that example there, we took then 32 parameters, each parameter for one of the braces, for the stiffness of the braces, and then testing each of the 32 parameters for different damage cases. And the red arrows are where the actual damage is. So the test reacts then for the parameters that are actually damaged, actually changed. So that's just on one data set, on one damage data set, on the left and on the right. Okay, so this was one framework for the statistical damage diagnosis. And now I want to present a second framework that is based on the Kalman filter, also for the purpose then of damage diagnosis. So where we can exploit the properties also of the Kalman filter itself and of residuals and their asymptotic properties for actual damage diagnosis. So we have a very similar structure actually, but with quite a different basic concept for the damage diagnosis. So what we do here is actually to evaluate or to parameterize the innovation of a Kalman filter in terms of our damage parameters. And for that, we first formulate an additive fault detection problem, because there we can link our changes in the system or changes in the parameters directly to the properties of the system. Then in the second step, we parameterize the innovation of our Kalman filter in terms of our damage parameter, and again make a generalized likelihood ratio test then for the testing for changes. Yeah, and for that, for the additive change detection problem, we use these strategies here because there is in the automatic control community, there's also quite some literature exactly on those problems that look like that. So we have some system matrices in the reference state A0 and C0, and if there is a change in the system that is defined by a parameter change delta, then some additional terms in our state space model get activated. So in the reference system, our delta equals 0. So we have a standard state space model. And if there is a change, there is a fault happening, then those two terms get activated. And those matrices psi k and phi k are then called the fault profile matrices that describe how the change in the parameters acts on the states and on the outputs of the system. And then, we need to decide if our delta is 0 or not. And that's used heavily in the control literature also, for example, for describing like actuator faults in the state equation. So the psi k can, for example, correspond to actuator faults of the system. Sensor faults can be described by the phi k if some faults happen in the outputs. But here our problem is quite different because we are looking at changes in the dynamics of the system and they're linked into all fault parameters. So there are changes in matrices A and C. It's not so direct as here it is. So, and we have a multiplication between A and the state. So if there is a fault in A, if there's a change in A, we have a multiplicative problem. And so the first purpose then here is to transform, well, our problem of detecting changes in the dynamics of the system to this kind of additive change detection problem. And that's done under the premise then that all faults are small, again, that we have small changes. And for that, then we need our Kalman filter. So we set up in our reference system, we set up a Kalman filter that we run on our new data and get a state estimate xk0, assuming then that we're in the reference state. Taking the Kalman filter, assuming that we're in the reference state. So we make a perturbation analysis then to obtain our fault profile matrices by k. Okay. So we assume that our change in the system is small, so epsilon is something small. If the change in the parameters is small, then also the perturbation of our system matrices is small. We can link our system matrices to our damage parameter through their eigenstructure, and the link of the eigenvalues, eigenvectors, then to our fault parameters, because our structure parameters are linked to the eigenvalues of the system, eigenvectors of the system. And since we assume a small change, we can also see that the state in our current system is a perturbed version than the perturbed version of our state that we estimate from the Kalman filter, even if the filter is from the reference system. So if you just put all of that in our state space equation of the current system, we can actually compute them by perturbation analysis then our fault profile matrices psi k and phi k. So they depend on each time sample, which again depends then on each of the Kalman filter state estimates xk0. So one can make such a transformation then neglecting the higher order terms than in the approximation. So that's a technical part. Those matrices, they can be computed based on the Kalman filter. And then based on such a system, we actually can analyze the properties of our innovation, computed then from the Kalman filter of the reference system. Yeah, so if our system is in the reference state, the innovation has a zero mean. If our system is not in the reference state anymore, our innovation will be biased, because Kalman filter is not optimal anymore. And one can actually compute the mean of the innovation in the damage state if our system is damaged, because we have all those links with our fault profile matrices to the damage, and iteratively we can implying then the fault profile matrices psi k and phi k in our system matrices from the reference state. One can actually compute then the mean of the innovation with that sensible. So JK is a sensitivity to describe the mean of our innovation, and use then that similar as before to test, well, is our mean zero of the innovation or not, to get then the damage diagnosis. So like that, we end up again performing the generalized likelihood ratio test. Yeah, we end up with the test statistics that depends on our innovation. And on yeah, the JK, the sensitivity of our innovation mean to the parameters of the system. Now they are computed for each sample because they depend on the Kalman filter states that we have. So we get a test statistic, and if we sample those terms, if we just stack them in vectors, we get the same structure of the test as we had before in the previous framework. So the properties, the statistical properties of that are actually very similar then for the evaluation. So we have also an approximately k-square distributed test statistic with an uncentrality parameter that depends on our change in the system. But we start with a different premise, so we can use here properties of Kalman filter and don't have the asymptotic evaluation of the statistics as we have before. So here are some simulation results. The first one for the detection of changes in the Monte Carlo setup. So here we compute our test statistics for the reference state and two damage states of the Mars spring chain, where we have the distribution in the reference state. From there we can set up our threshold, and we have distribution into faulty states that are getting more and more separated, while the bigger the damage is then. And we can do the same strategy then for the damage localization by testing our structural parameters, each one for a change. So here we have a 2% stiffness reduction in element 2, and having the test for all 8 elements because we have an 8-element Mars spring chain. Then here we have a test for we have a damage in parameters 2 and 4, where the test reacts, and the other ones are declared as non-damaged. So to recap, so for the damage diagnosis here, we have two statistical frameworks. The first framework was based on asymptotic evaluation of data-driven damage-sensitive features that can be quite general, but there we need their asymptotic statistical analysis that can also imply then quite big matrices concerning their covariance, for example. So if our feature is big, then covariance matrices get big and maybe problematic to estimate. Yeah, but we have quite some experience with those tests and applications are fine. While the second framework is a more recent addition that is based on the Kalman filter innovation, needing then Gaussian noises in theory for describing the statistical properties. But then it inherits also all the nice features from the Kalman filter. So we don't have asymptotics. The innovation covariance is quite small, depending on the number of sensors that we have. So there are advantages also in their applications. Then in both frameworks, we consider sensitivities, or we can consider sensitivities towards our damage parameters. So to make a link to the FE model being based on the data for the tests. And like that can come up with test statistics for damage detection and localization. So the benefit of those frameworks is that we can actually very well characterize our probability distributions of the tests, as well as in the reference state, as well as in the damage states, because we know the chi-square distributions, we know how they depend on our damage parameters. So like that, we are able to set up theoretical thresholds to distinguish the states, for example, and more importantly, actually to predict also test reaction under damage, and being able to predict to some extent the probability of detection then under damage. So in that sense, we are able to analyze also the damage detectability, for damage occurs of the system, to analyze the performance of the methods, then still under small changes in the system, because we're always interested in the beginning of the damage and to be able to detect small changes. So for that, I want to finish with some considerations regarding then the detectability. So here we ask ourselves the question then, okay, if I have sensors installed on the structure with some SHM system, what damages can we actually detect, or which damages will be visible from the sensors then with the chosen damage detection method and with the chosen sensor setup? So which damages and how big do those damages have to be reliably detected then? And for that, our statistical framework, since we know the probability distributions, we can define then those terms like detectability of damage, or what does it mean then for those methods. So if I want to reliably detect some damage, well, then the distributions in the reference state and in the damage state, well, they have to be well separated up to some extent. So if our non-centrality parameter then of the chi-square distribution is above some minimal value, well, then we can define the separation like that for having a detectability. And that minimal value then depends then first on our acceptable probability of false alarms. So where we put our threshold of the reference state, and it depends on the probability with which we want to be able to detect our damage. So the probability of detection that is, for example, code-based. If we want to define just the term what is what do we mean with the detectability of the damage? So we can define this parameter. Then once we have this information, we can define our minimal non-centrality for the separation of the distributions then based on our non-central chi-square distribution properties. And once that's done, we know that the non-centrality parameter in those methods is described by the change delta in the parameters, well, that is rated with the square root of n, and that it depends on the J on the sensitivity of our used residual with respect to the damage parameters and its covariance sigma. So now when you want to analyze how big does a damage have to be in a single parameter, for example, at the hotspot of the structure, we want to see, okay, how big is the stiffness loss in that element, or how big does the stiffness loss in that element have to be in order to be detectable. We analyze a single parameter change and just solve for the difference between delta H and delta H0, so between the difference of our parameter in the damage state and the reference state, and have a very simple formula for that. And so we have so that indicates us how big is the change in the parameter that will be detectable, and that depends then on the data length, for example. So if we have more data, then we can detect smaller damages. I mean, these are quite trivial connections, but it's nice to see them in one simple formula. If our parameter has a big sensitivity from our residual, well then we are very sensitive to changes in the parameter, or the changes therein are smaller also to be detected. If we have less noise, so if our sigma is smaller, then the inverse is bigger, 1 over the inverse is smaller again, so if you have less noise, then we have better detectability, and so on. Yeah, and that this works, that this can really work in the experiments also, for that we have an example on a beam where we added masses. So that beam, we discretized it in 9 segments, where we added a mass once at a time. So we have 9 mass parameters. So adding mass was easier than cutting through for the experiments. That's why we chose the mass parameters for validation, and made then a Monte Carlo setup. So where we recorded very long data sets in order to be able to have many data sets to actually evaluate also all distributions. And the first part was then to check, first in a simulation study, how big each of the 9 parameter changes have to be detectable. Then we applied this parameter change to the model and made a Monte Carlo simulation to check if we really have the according distributions. And for all the 9 parameters, we can see here that this works quite nicely. So we set up a target POD, a target probability of detection of 99%. And for the applied images, we get them the histograms each time. So for example, in element 1, we need a change of mass of 8.7% of the mass of the element for ensuring detectability with the sensors that we have in the structure. And the histogram is then the coming from the generated data under this change, and it matches quite well the target distribution that we wanted for. And we can see also that, okay, in some elements we need more damage to be visible, in some we need less. So every parameter change has its own impact on the residual. And it also works on the real data, where here since we had fixed masses, we actually tuned the measurement length such that our mass that we had available is just detectable with again the target of the 99%. And we can see then that for masses on element 8 and masses on element 5 that we put here, I mean the lengths are a bit different then, but the distributions still match quite well also on the real data. So to recap, so the first outcome of this then is that our theoretical distributions of the test statistics that we have from the theory, that they are quite reasonable, then still assuming all small damage. To evaluate our minimal detectable damages, we need measurement data in the reference state, well, either from simulations or better from real data if we want to consider the real noise properties of the data. And we need our sensitivities of the used damage residual with respect to the damage parameters. And then the prediction how damage is detectable in the structure is based on this reference data and the FE model, considering in particular the uncertainty in our damage sensitive features that are computed from the data, and the sensitivity of course towards the damage parameter, and then all kinds of SHM system properties like the sensor positions where the sensors then see our data and can see the damage, noise properties, and so on. And then we can use that, for example, also as an input to obtain an optimal sensor placement that can achieve optimal damage detectability. So we have a performance criterion in that sense then for the damage detectability. We can use that also for analysis of damage localizability, where in practice we have a bit of a different problem where we want to analyze changes for the different parameters of the structure. And I mean, from an FE model, we usually get tons of parameters, so we cannot distinguish all of them. So we need to do some clustering, and can optimize such a clustering then based on sensitivities and the uncertainties. And PODs, the probabilities of detections that we can predict then from the method, or can also be used then for Bayesian updating of failure probabilities, for example, because there, well, we need PODs, or we need to have an idea of PODs then for different damage states of a structure, or as input in SHM value of information analysis. All right, to conclude, so in our works, well, we consider statistical uncertainties for modal analysis and for the statistical frameworks for damage diagnosis. Those methods have then, quite a strong theoretical background and thus predictable performance in practice. And we focus on fast and memory efficient implementations, well, to be feasible for the real data also, and have validated on several case studies in the lab and in the field. So what we are concerned now is then also, in particular, further exploration of the Kalman filter-based framework, because that's also quite a recent addition to the family of damage diagnosis frameworks, and to explore more also then, well, how we can use our damage diagnosis results and the properties of the statistical properties of those damage diagnosis results then for actual monitoring-based reliability assessment to move a bit forward also to the remaining life prediction. So last but not least, I mean, this is not work that I've done all of my own. Just to acknowledge, the IFRS team in particular at INRIA, with the head of the team, Modal, and time, all the PhD students and Simon, with whom I did that work, and the collaborators at UBC and SVS. So thank you very much for your attention.